History. Okay. So where were we? Let me make this bigger. So the last thing we were looking at is substitution. Let's go back to that. So okay, so we were here, right? So we were said again. Should I make the syntax a little bit bigger, perhaps? I'll make it bigger. So this should be readable. If not, just shout, right? So I can make it even bigger if you want. Okay, so what were we looking at? So we were looking at syntax, right? So the thing that we were focusing on is studying the syntax of um, just the simple arithmetic expression language, and we were trying to prove certain properties on the syntax. The syntax properties sort of intuitively hold, and we are looking at more and more complicated ways of thinking about simple proofs that we can do. And even though the proofs are simple, the thing to take away from this lecture has been also previously is that the way to use Fox tactic language, right? And in particular, we were using the Frapp books library of tactics, and that's what we were looking at in the last class. We'll continue doing that in this class as well. So, okay, so we are looking at this substitution function, right? That's a recursive function that takes an arithmetic expression and then for a given variable replaces that with another arithmetic expression, and you get that substituted expression as a result. And we saw the definition of this in the last class, and the thing to remember is that we use this double equals v, and what it's doing is that it's doing a string comparison here. Its type is actually far more expressive, but that's not important here. All we are doing is we are doing equality on strings at this point. If the strings are equal, then it returns true, otherwise it returns false. Okay, so once we have the substitution, right, we can go ahead and prove a nice property about substitution. In particular, we are proving a property about how substitution relates to depth. Okay, so what this theorem is saying is if you substitute in this expression for some variable with this expression, the depth of that expression is going to be less than or equal to the depth of the original expression and added with the depth of the expression which you are substituting, right? So if you think about this is intuitively true, right? So we are replacing a variable. We have a tree. Our expression is a tree, and we are sort of replacing a variable somewhere. So if we easier case is if we replace the variable somewhere high up and the depth is sort of greater on some other side. If you replace it, it's not going to change the depth, right? The maximum depth is the height of the tree, and that's not going to change because of the replacement. And obviously, that is going to be less than or equal to. I mean, it is equal to the depth of this in this, so it is less than or equal to depth of in this plus depth of with this. And observe that depth of an arithmetic expression is at least one. If you go back to the definition of depth function, for constants and variables, it is one. For plus and times, it is one plus the maximum depth of the sub expressions, right? So it is going to be at least one, and hence you will you can sort of see that this theorem should hold, right? So that's the intuitive understanding of why this theorem should hold. So we are using these sort of reasonings, right? Oh, I know that the depth of the thing that you're substituting should be at least one. And hence, you have these cases in which we can show that depth is going to, this theorem is going to hold. So this is one of the first theorems where you sort of, where I sort of found that, okay, this is, I can informally prove this, right? I can work through cases and I can informally prove this, but I really want to have like a mechanized proof, which is what we are doing. We are mechanically proving using the proof assistant that this theorem is in fact true, right? If you prove it using Coq, you have no doubt at all because you have a proof term in your hand. Right? Do we believe that? I mean, of course, this is going to be proved. So, what do you think, right? Do you believe that this theorem intuitively holds when you look at it? Right? What's your feeling? Crickets. Anyone? Anyone thinks this theorem would not hold, right? That's a valid thing to have as well. Everyone thinks this theorem would hold. Okay, that's fine. So we are going to prove it, right? So let's see how to prove this property. So we essentially have so we start the proof, right? What do we have here? We have expressions in which we are sort of substituting, right? And basically, the idea is that we are going to do induction on this in this variable. And why is that? Because there are going to be multiple cases for the expression in which you can substitute. We're going to apply induction on that, and that's the natural place to apply induction here because we are inducting on the shape of the expression in which we are substituting. And let's apply induction on that. Observe that one thing to observe here is I'm not introducing these for all variables, right? I'm just sort of directly doing induct on this, induct on in this variable, and induct is clever enough to do the introductions for us. So we have four cases thanks to the four constructors: const, var, plus, and times. And plus and times are going to have induction hypothesis as well because we have a sub expression, right? So what do we do as we do, right? So this is for a particular constant, and if you sort of look at substitution for a constant, right? So if you're substituting in a constant, you just get that same thing back, right? So if you simplify this, you get the constant n back for this term, right? And depth of a constant term is 1. So if you simplify this, you're going to get 1 less than or equal to sum of, successor of depth of width this. And this particular property is always going to hold because by definition of depth is at least 1. So if it is at least 1 and you add 1 to it, then it is less than or equal to 1. Right? So actually, you don't even have to look at this, right? So even if this is 0, if you look at the type, that's a natural number. So even if it is 0, this is 0 plus 1, so 1. 1 is less than or equal to 1. So you don't have to do anything here. So linear arithmetic makes it go through. Right? And the next one is the variable case, right? Variable case is the interesting one because we have two cases, sub cases here. So the variable that you're substituting is the variable that you're replacing, right? If that is the case, then you actually do the substitution. Otherwise, you return the original expression, which is just var of x. Right. So we have usually so far what we've seen is we have had inductive data types with multiple cases, and we've done case analysis. So now you have a if then else, right? And we also are going to do case analysis there. When you do the simplification, you see that this basically brings in the if then else, right? And we have two cases here: one where this is true, in which case we have to do this; other where it is false, and we have to handle the else case. And cases, the tactic that we've been using as a stand-in for, actually, have we done cases before? No, we haven't done cases before. So cases tactic is very much like destruct, right? Wherever you can apply destruct, you can apply cases. And the thing that it does is it does case analysis. So if you have a some data type, right, which has multiple constructors, it will introduce one case for each one. But it's also a little bit more powerful in that if you have expressions which are in the which are predicates for if then else, then it breaks that into two cases, right? The possible values here are this is true and this is false, right? So either x equals replace this or x is not equals this, in which case you have to prove both of the sub cases, the true case and the false case, and cases will allow you to do that, right? And the thing to remember is cases is from the frap library. It's actually a very powerful tactic, and it sort of bakes in destruct plus more, right? And again, as I mentioned before, the way to learn these tactics is by examples, right? Don't try to um, I wouldn't say don't, but it is not useful to actually look at what are all the things that cases will do, right? So learn by examples. We can go back to what are all the things it will do after you learn how these tactics are built up. Anyway, so you can do case analysis on this predicate. And what we are saying is essentially the way to read this is there is a true and a false case. So I'm going to analyze both cases separately. So you have three sub goals here. And when I do case analysis, it comes to 4, because in the first case, I'm going to assume that uh, the case is true. X is equal to replace this. In this case, you don't actually have to appeal to this fact that you learned from the predicate, right? If you just look at this thing that we want to prove, it says depth of width this is less than 1 plus the depth of width this, which we know is true. So linear arithmetic makes it go through. And here we know that the depth of var is 1, right? So if you simplify, you'll see that the depth of var is 1, and 1 is less than 1 plus anything, any natural number. So linear arithmetic makes it go through. So here we have the inductive cases as well, right? We have depth of substitute of in this replaces with this less than in this one, in this two. In this one, in this two are the variables that are obtained by the sub expressions in plus, right? So plus has two sub expressions, and that is what that is precisely what we have here, right? We have E1 and E2, and in this one and in this two are the names that Coq has automatically chosen for us. So we know this holds thanks to the induction hypothesis. You can just simplify this, in which case you get this complicated expression with um, depth of substitute of in this one, replace this with this, right? And which is what you have here, right? And similarly for this one, you have the same expression here. And if you sort of spend time and read this in detail, right? So you sort of do replace that with some x and replace this with some y. If you substitute it, you will see that thanks to these two induction hypotheses, these two assumptions, this will always hold, right? And linear arithmetic knows this fact, so you can make this go through with linear arithmetic. And the last case is for times, right? Times expression, and this is exactly the same as plus. So this also goes through, and we are done with the proof. So we proved that this particular theorem holds, and now we don't even have to hand wave and provide any incomplete proof, right? We have a proof that this property holds. Any questions on this so far? Okay, if there are no questions, we can actually prove a stronger property, right? And the property that we are actually proving here is, here we have a less than or equal to, right? And the observation here is, we know that the depth of the variable, depth of something that we are substituting is always going to be 1 or more, right? Even in the worst case, right, where you sort of replace one variable with another variable, right, the depth of the substituted expression is not going to change. So this will be the same as depth of in this, because say I have an expression which is just variable x, and I replace that with another expression which is variable y. right? The depth hasn't changed. But the fact that I'm actually adding depth of the expression I'm replacing with, which happens to be y here, I add a 1, right? It is at least 1 greater than the worst case in which the depth hasn't changed. So we can make this theorem actually stronger. We can replace this less than with less than or equal to with less than, right? Which is what we are doing here. This is the same theorem, except that I'm replacing less than with less than or less than or equal to with less than. Okay, and how does the proof change? So again, I'm going to do induction on this. I have 4 cases. I do simplification, and now it gets interesting, right? So if you look at where we were at the same position last time, so I have 1 less than or equal to 1 plus something, right? And this is true because even without knowing anything about this term, I know that that it's going to return a natural number, and the smallest natural number is 0. So 0 plus 1 is less than or equal to 1 is less than or equal to 0 plus 1, right? But this is no longer true here, right? So let me go to the same place here. Yeah, so the obligation, the proof obligation now is 1 is less than 1 plus depth of width this, right? So without looking at what this function does, right? So you cannot show that this fact holds. Why? Because in the worst case, this could be 0. So in which case, you will have to show that 1 is less than 1, right? That doesn't hold. So linear arithmetic cannot magically make this go through without looking at the definition of what this width this is, right? And and we know by looking at the definition of width this depth definition, right? We are applying depth of width this. So if you go back all the way to depth, we know that the depth is at least 1. So if you do case analysis on depth, you will find that the depth is going to be at least 1. So if you just do simplification there, things will just work out, right? So that's the idea that we are going to apply, right? So we are going to case analyze with this, and we are going to find that it is going to be at least 1. Hence at least 1 plus 1 is going to be at least 2, at least 2. So 1 is always going to be less than at least 2, and that's the reasoning that we are using here. And the way we are doing that is we are applying. I would recommend just stepping through this yourself. All I'm doing is I'm doing case analysis. I'm simplifying the expression, and I'm just making that go through linear arithmetic. So I'm not going to show you individual steps. The way you do that, you know it at this point, right? You do cases, it will produce four other cases. You do simplification, look at linear arithmetic, and that will go through. So that's the only change in this proof, right? And the change is that we have to now prove a stronger property. So we have to look at what this with this variable depth of with this um, definition gives out, and it gives out a value that is at least 1, and that is what makes this proof hold. I think the rest of the proof is the same. You get to this similar condition again once more here, right? And we use the same tactic as what we used earlier, which is case analyze this with this expression, simplify linear arithmetic, and that makes it go through. And these two are just the same. So what we've done now is we've proved a stronger property on substitution with depth. Questions on this? How we proceeded with this? Okay, no questions. So maybe you're getting all that I'm saying. So let's pick up the pace, right? So okay, so here is so the thing to remember in Cork, right? It can get very tedious if you don't. The proofs can get very tedious if you're not smart about how you encode the proofs. In particular, Cork has a lot of support for automation, right? We did cases which is doing a lot more than destruct, for example, and we did induct, which is doing a bit more than induction, right? When you do induct, it is automatically doing the introductions and so on. So I mean, these are very simple cases, but again, we saw simplify, we saw linear arithmetic, right? All of these are built out of more fundamental tactics. And the way these tactics are built up is like rich language for metaprogramming in Coq. In particular, all we are doing when we are sort of writing tactics is we are taking some functions that applies those functions and does syntactic transformations, right? And when you transform syntax terms with syntax, that is known as metaprogramming, and we are not going to look at metaprogramming that much, but here is an example, right, which is going to automate the proof for not automate, but make it even more shorter, right, than what we had done. So what we are going to do here is we are going to take the same theorems as before. So this is the same property that I'm going to prove again here, right? It's the same property. It might be a little bit unreadable, but just focus on this term. It's the same thing. And what I'm going to do is I have a lot of repeated tedious tactic application here, right? So I first inducted, and then first case was simplify arithmetic. Third and the fourth cases were simplify arithmetic, right? And the second case I had to do cases, right? That was the difference. And then arithmetic made it go through. There is also a simplify arithmetic for the second of the cases that was obtained by doing case analysis. So what I really want to do is to say, okay, for all of the cases, do simplify arithmetic. But for the case where you have to do if then else, right? Go and do this case analysis there on the term with the if, right? So you can instruct Coq to do this using tactics, and here is how you do it, right? So um, so we are going to use some special syntax, right? And we are also going to do some really nice operations. So the way we start off this proof, right, is by doing induct in this, similar to what we had done earlier. We are also going to do simplification, right? So what this is going to do is to generate 4 cases, and in each of those 4 cases, it has done simplification, right? And the thing that we want to do is to say, okay, there is this one case which involves the if then else, and for that particular case, do a case analysis. Sorry, do a case analysis on the predicate that is in between if and else. And Coq has this excellent way of pattern matching on the goal that you're proving, right? So when you do induction, right, you have these 4 goals, right? And Coq allows you to essentially pattern match on the syntax that is here, so that you can find out some properties and apply certain tactics only on certain goals that satisfy a pattern. In particular, if you do this, right, and then you come here and simplify, in this goal, there happens to be a if then else, right, in the conclusion. Let's call it the conclusion for now. The whole thing is, we'll call it the goal, right? These are the assumptions. This is the conclusion, right? In the conclusion, I have an if then else, right? No other, in none of the other goals, the conclusion will have an if then else, right? And if you see an if then else, what we are doing is we are doing case analysis here, which is what we are doing here, right? And this is what I want to do in the shorter proof, right? And the way I do it is, and the way I express to Coq to do that is this way. So I take the goal, right? So I have a semicolon here. I inducted, I simplified. So for each of the goals, 4 goals, I sort of, I'm going to apply the next tactic, right? So let's start from here. So I'm going to match with goal. So goal is this variable that is in the environment, right? That is like a global thing that is sitting out there. And goal represents the term that is the current goal. And when I say goal, it includes all of this, right? It includes all this. So it includes a set of assumptions, and it also includes the conclusion. And what I want to do is to say, For the goal which has the conclusion with if then else, go do case analysis on the predicate, right? And the way you do that is using this match with on the goal, right? You pattern match on that. How do you pattern match multiple assumptions and conclusion? So Coq has again special syntax for that. So the syntax here says that anything on this left-hand side of bar minus, right? You assume that as assumptions. So this bar minus is sort of standing in for the entails that you would have seen in your logic classes, right? P entails Q means under the assumptions of P, Q holds. So that is the entail symbol. So the way we are just reusing the entail symbol. So anything that appears on the left-hand side, you sort of think about that as hypothesis. So here I'm not naming any hypothesis. I'm not pattern matching any hypothesis. It just means that hypothesis could be anything. For the goal, for the conclusion, right? This is anything on the right-hand side of this entail symbol is the conclusion. For the conclusion, right? There will be a sub expression, right? So not the entire expression is if then else, but there is a sub expression here, right? Which is if then else. And this context is another global variable that is sort of saying you sort of read it as looking for a sub expression in the conclusion that matches this precise syntax, right? And we do have a sub expression that matches that, right? And what we are saying is look for a if then else sub expression, and we are using question mark a and question mark b here, and these are known as meta variables. So these question mark a and question mark b are not looking for a and b. These are like placeholders for a and b, right? And this question mark a will be bound to this x here, right? And question mark b will be bound to replace this here. We are actually operating on the syntax, right? This is why I meant this is meta programming. So when you have a goal whose conclusion has a sub expression, which is if then else, where you bind the left hand side of the equality with the a and right hand side of the equality with b, we are going to do case analysis on that predicate, right? For that particular matching goal, go and do case analysis, right? And also do simplification, right? And that pattern match ends here. So that is precisely what we are saying here. But if you look at how tactics are, how tactics work in Cork, so they always succeed or fail, right? Sometimes you might just ignore it. So simplify, for example, if it is not able to simplify, it just says, I'm just going to not do anything. I just return it as a success, right? So typically, when you apply tactics, the same thing holds for auto as well. If you apply auto, if auto makes the goal go through, then it says, okay, the goal is done. Otherwise, it just says, I give up, right? But this is not true for something like trivial or equality. If I just apply trivial here, right? Yeah, actually, trivial also says this. Maybe equality. Yeah, I don't think we've seen equality. Anyway, if you apply equality, equality is a tactic, right? I don't remember whether I introduced this earlier or not. Have I introduced equality before? Anyone?
No, sir.
Okay, fine. Think about equality as some more powerful trivial, right? The takeaway, the main point that I want to take away, the tactic itself is not important here. The thing is, tactics will either succeed or fail. And what it says here is that that particular tactic has failed, right? So, because equality, you can't just prove this with equality. You can't just prove this entire goal with equality. We have to apply induction. That is why this has failed. But you can sort of make this failure into a soft failure, right? So, by applying this tactical called try, all try says is try this equality tactic, right? If it succeeds, then okay, that's fine. If it fails, just ignore the failure. So when I do try equality, look at this one. The actual proof state hasn't changed, right? This is the thing here. The state hasn't changed, except that the failure is gone, right? Earlier it used to fail saying, oh, tactic failure, congruence fail. So try is this tactical, right? Which sort of converts hard failures into a soft failure. And why is try important here? So I'm applying cases and pattern match here, right? This match with um, only applies for one goal. For all of the other goal, it doesn't work. So that's why I need to prefix this with a try. This entire thing is a tactic. Okay, when I prefix something with a try, it simply says, oh, if it works for a particular goal, then go ahead and do the simplification. In particular, do the case analysis and simplification. For other cases where we don't have this if then else, just ignore the failure, right? And that is precisely what this try is saying. We've done the case analysis. We've done the simplification, right? If you go back to the proof structure that we had earlier, we've done the case analysis. For one of the cases, we need simplify. And in all of the other cases, we simply do linear arithmetic, right? So this is the first, just to go back, for the first one, you do simplification, linear arithmetic, that goes through. For the second one, you do simplification, case analysis, and then linear arithmetic makes it go through. Again, simplify and linear arithmetic makes it go through. Simplify linear arithmetic makes it go through. Simplify linear arithmetic makes it go through. So the last thing that we need to do here, right? So we've done all of the things that we needed to do. So we've done induction, we've done simplification, we've also done case analysis on this one goal, right? We've done simplification for the resultant sub goals. The last thing is linear arithmetic. So this applies to all of the goals, right? Because I've been using semicolon. I've not been using a dot anywhere. So this is also a semicolon. So what this does now is it makes the entire proof go through in a single tactic. And what we've seen here is a way to write very short tactics, right? Usually the thing is when you write an interesting function, there'll be one or two interesting cases. And all of the other cases will be like, oh, trivially true, trivially true, trivially true. And this way of writing this match with goals, right? We won't do much of this in this course. You can use this, right? Again, as I mentioned, you can write proofs even very explicitly. That is also fine. But what I want you to take away is that there is this nice way of manipulating syntactic things, analyze the syntax of what terms that you have, so that you can write very short proofs, right? And here is one example of doing that. Right? Any questions on this? You'll have lots of questions, but start with questions, and then we can see how far we get. Why is there a semicolon after? Why is there no semicolon? Oh, that's the end, right? So if you just write semicolon here, it will just expect another tactic. You can write trivial, whatnot, but semicolon just says there is more coming, and dot is the way you end a particular tactic, right? And this whole thing is sort of saying I'm just doing a single tactic. So if I start here and I do one step, it goes all the way to the end because I'm combining multiple tactics with a semicolon, and that's the reason why there's a dot at the end of linear arithmetic. Okay, good. Any other questions? No other questions? Okay, fine. So this is sort of an advanced way of writing proofs. We will see some of it, right? We won't do much of it later, but this comes in very handy when we do complicated proofs. So here is one silly theorem that just says if you replace a variable with itself, right, nothing happens. And this is obviously true. We know thanks to the way it is defined. You want to make the obvious proof also small, right? You don't want like tedious proofs for obvious things. And yeah, so if you do induction, if you do simplification of each of the terms, there'll be 4 cases, right? And equality will make it go through because of equality will. Oh, we haven't seen equality. So equality is like I thought we saw equality earlier. Let's see. I believe we introduce equality. Yeah, we introduced equality earlier, right? When we did this commute of a commute gives you the same expression. So equality is like is like trivial, but also does a lot more in terms of proving equality. In particular, it does reflexivity, symmetry proofs for you automatically, transitivity, um, all of which trivial does not do. Trivial only does trivial proofs, right? Um, uh, if it is reflexive, it goes through. If it is, it doesn't use symmetric. If you have x equals y in the assumption, I believe this is true. If you have x equals y in the assumption and you're trying to prove y equals x, trivial might not make it go through. And again, transitivity, right? So if you have x equals y, y equals z, and you want to prove x equals z, trivial might not make it go through, and equality will make it go through. Equality will also quantify constructors. If you have for all n, x of n equals y of n, and then you have x of 5 equals y of 5, which is what you want to prove, then equality will also instantiate those quantifiers automatically for you. Um, so think of equality as a bit more powerful than trivial, right? And wherever you can use trivial, we will just keep using equality, right? Uh, yeah. So okay, so we have introduced equality before. We are going to do equality again, right? In this proof, um, we are showing equality, right? So we have equality here. We have a less than or equal to earlier, and that's why we are using linear arithmetic to go make it go through. But otherwise, the proof is sort of the same. You can step through it by yourself, but the point of doing this is not to show something very awesome, right? We know this is true. Here is a way of automating this proof. The structure of the proof is very similar, right? These three things are the same up to here, and it's only the last one that differs. So we are doing equality here. We did linear arithmetic earlier, so this proof goes through, and yeah. So another theorem, which also leads to a which can be proved with the same proof as earlier, is that if you substitute a variable, right? If you do the substitution and then commute, it is the same as first commuting, right, and then doing the substitution. So if you do the substitution and then commute, right, it is the same as first commuting and substituting for the variable with the commuted term, right? This is the key thing. So if you just do with this won't go through. The term that you're replacing should also be commuted, right, before the replacement. And this sort of is sort of hinting at the fact that the substitution and this commutativity of the terms, right, do commute. These two independent operations, substitution and commute. You can apply substitution and commute in any order. And the proof is very simple. Proof just is a direct application of this tactic, this try tactic with pattern match on if then else, where we do cases. Okay, so let's move on. I mean, I would recommend you to step through this, but I don't think there is anything very interesting there. So let's do. I think this is the last example in syntax. So we are doing constant folding here. So constant folding is like a very standard optimization in compilers, right? And the compiler can statically see that you are, say, multiplying unknown variable with a 0. What it will say is, oh, I know multiplication yields 0, so I'll just replace that with 0, introducing further more optimization opportunities, right? And we have a very simple language, so we are going to start apply constant folding there. So it's a recursive function, right? So it takes an arithmetic expression and it returns an arithmetic expression where the constants are folded. And what you do is the interesting cases are plus and times, right? In plus, if you have E1 and E2 and you get E1 prime, E2 prime, which are constant folded expression of E1 and E2, observe that I have a let here. So the let syntax in Coq is very similar to OCaml, except that you have to use colon equals, right? Because equals, the plain equality is taken over by this propositional equality, right? When you want to write A equals B in the theorems, that is taken over. So we have to use colon equals. We can take this over because the colon equals is the syntax that we use for reference assignment in OCaml. We don't have mutability features in Coq, so this is fine. So all we are saying here is if E1 happens to be 0, right, and I'm adding a 0 to some expression, it is the same as the other expression, right? So I'm adding E1 prime happens to be 0. I have E2 prime. So this is just E2 prime. And similarly, if E2 prime is 0, right, and E1 prime is some term, then I just return E1 prime. So, but if you know that E1 is a constant, E1 prime is a constant and E2 prime is a constant, then you can, at compile time, right? This is sort of, you can sort of, even though we have not even seen interpreters yet, you can already see that you can compress certain terms, right? By while preserving meaning. Again, we've not seen what the meaning is, but intuitively, right? So if you have a constant here for one expression, constant for the other one, you can replace that with a single constant where you do this addition at compile time, right? So you can add these two variables and get the term that represents the sum of these terms. And similarly for times, right? If these two are constants, then you can replace that with the product, right? If it is one of the terms is 1, then you get the other term, 2 cases. If one of the terms is 0, then it doesn't matter what the other term is. You just get a constant 0, right? And of course, we have the base cases, right? If none of these cases apply, none of these optimization cases apply, you just replace the same thing with plus E1 prime plus E2 prime, so that you get, you leave the terms as it is. Okay, so that's constant folding. Okay, so it's a non-trivial function because it has like 1, 2, 3 optimization cases here, and then 1, 2, 3, 4, 5 optimization cases in times. And you may want to show that constant folding preserves certain properties, right? And here is a simple example, right? So I have a term which is 0 plus x times 1, right? If you add 0 plus x, that gives you x. X times 1 is x. And we know this statically, right? Even without evaluating the term, we know this holds. And here is what we are going to do, right? When you apply constant fold, you will just see that this whole expression has just reduced to variable x because constant fold does the right optimization. So one thing that you can show in constant fold, right? What's the whole point of doing constant folding? We are trying to reduce the size of the program. We are also trying to reduce the number of, if you sort of imagine what the program has to do, right? When you compile the program, you will have a set of instructions. And what the compiler is trying to do, among other things, is to reduce the size of the program that is emitted, right? If you reduce it, which means that you have fewer number of instructions, your program will go faster, right? And this is precisely what we want from constant folding, right? If you have a AST and you apply constant folding, it should not increase the size of the program. If it does, then you're doing something wrong, right? And um, that is the theorem that we capture here. So for all expression, if you constant fold the expression, then the size of that resultant expression is less than or equal to the size of the original expression. Right? This is the intuitive nice property that we want from constant folding, right? And we can sort of try to prove this. So here is a very explicit way of proving this, right? So we have only one term here, the E term. Let's basically apply induction on the structure of the term. So you'll get one for each of the cases, and then you have to do yeah, you might want to apply induction as well. So you have four cases. For the first case, if you simplify, 1 less than or equal to 1 linear arithmetic that goes through. Then again, if you simplify for the variable case, 1 less than or equal to 1 that goes through. Here is plus, right? And you have a constant fold of the subterms. If you simplify, you get this big expression, right? And the thing that you want to observe here is, so there are pattern matches, right? There were three cases for plus. So one here, yeah, okay. So for the way it's sort of folded, this one pattern match with E1, E2 is it sort of expanded it to yeah, expanded that to separate pattern matches, but that's fine. It sort of jumbled up this pattern match into a pattern match on E1 first and followed by pattern match of E2. So the structure is not congruent directly. But anyway, so the thing that you want to observe here is there is a pattern match, right? And there are three cases here. Again, you want to do case analysis, right? The way you want to prove this is, oh, let's assume that the result of constant fold of E1 is this case, right? And then let me prove that the property that you want to prove still holds. And let me do that for each of the cases. And at the end of the day, I know this is true. So this is the reasoning that you have to apply. And the way you do that is, again, use the cases tactic, right? I am using cases on the term that is between match with, right? And essentially what this does is it specializes the match width to one of these three terms, right? And it simply goes ahead and you have to do pattern match on each of the cases. So observe that you have one goal here because we are focusing here. But if you do cases here, you end up with four because you end up with four because this underscore involves two subcases. So the takeaway is that you can do case analysis on match with. So if you do case analysis, you get this further bigger term. Again, you see n, and one for n is 0, one for n is non-zero. You can do cases there, right? This is getting tedious. I'm doing this tedious proof because I want to show that this is tedious, right? And you have another pattern match here, right? Where E2 is some constant and E2 is not a constant. So let's do cases again, right? Lots more cases now, right? And one for each of the non-constant term has also been expanded. This is just too big, right? But at the end of the day, if you sort of zero in on the case and simplify, you will see that, again, I want to prove that 1 is less than or equal to s of the size of these things. And I know that 1 is less than or equal to size of E1, size of E2. So this property holds. So linear arithmetic makes it go through. You can keep doing this, right? And the thing that you should observe is the pattern. So what are we doing here? For every, we started with induction and then we simplified, right? All of the proofs go through with linear arithmetic. And whenever we see a match with syntax, we are doing case analysis on the term that is between match and with, right? And you can keep doing this manually. This is just too large, right? So this will keep on going. You can do case analysis. This is not a helpful thing to keep doing, right? So of course, you can prove the things like this, but the nice way to organize this is once you see the pattern, right? All we do is induction, simplification. Wherever you have match with, you do case analysis, and then you make it go through with the linear arithmetic, right? And that is what this simplified proof, compressed proof does, right? So induct on E, for each of the subterms do simplification, right? And then here is a new tactic for you. So repeat is a tactical that repeats a particular tactic over and over again as long as it can apply it, right? Until it fails, right? If it fails, it just consider that as a soft failure. But as long as it can keep applying the tactic, it will keep on doing it. And the reason why we have a repeat here is we are pattern matching on match with, right? We pattern match on match with, And for match with, what are we doing? We are pattern matching that in E, right? Whatever we have between match with, we are capturing that in E, and we are doing case analysis on E. We are doing simplification, and finally we do linear arithmetic. But the point is, if you sort of look at this proof structure, right? We did a case analysis on constant folder V1 that gave us a lot of sub goals, and on those sub goals we did case analysis on N. Again, we had a bunch of sub goals on which we did case analysis again, right? This is recursively trying to do case analysis over and over again, and we had one more case analysis on E2 here, right? And try tactic will not do the entire thing for us. We need repeat, because we do case analysis, and the case analysis gives us some cases. The subterms also have to do the case analysis again. So that is why we have a repeat tactic here. This keeps repeating until all of the cases are resolved, right? Which is precisely what we are doing. We are going drilling down to the base cases where we are doing recursive case analysis. We have a recursive pattern match. We have a recursive case analysis. And repeat helps us apply the same tactic over and over again. In particular, we are doing this. We are doing this case analysis on this match with, right? And if you keep doing this, you will eventually succeed, right? But here is a very nice short way of doing it, and this will sort of go through. Okay, this went through. That's fine. So we got the proof, right? And essentially, if you keep doing this, you will end up with the same thing. So the last thing that I want to sort of show is this commutation thing, right? Okay. So should I continue? Actually, I'll stop here, and then we can pick up from this one. This is also another example. It just introduces two other tactics, but I will do that in the next class tomorrow. So, any questions on what we are doing here? We introduce a new tactical, right? Repeat is not a tactic. It's a way to sort of apply some transformation on a particular tactic. You can sort of think about that as a higher order function that takes a tactic, returns a tactic, that does something more. Okay, so any questions on the stuff that we've seen today? No questions? Okay. So in which case, what we'll do is, I want you to go through this, right? So I really want you to step through this and sort of see how we have come up with this um, interesting application. There is no magic for coming up with short proofs, right? It comes with experience, but I sort of want you to see the pattern, right? How we might end up with something like this. And we will see one more example tomorrow. Again, I'll sort of show you how I develop this. Here I've shown you how I develop this step by step, right? Without using this repeat tactic. But in the next one, we will actually see how we sort of build this automated proof, right? Coq is very, very powerful. It's sort of has this rich language underneath, right? And just like any other language, you have to sort of practice with this and identify patterns so that you can use this in an effective manner. And this is one way of showing it. Let's see one other example in the next class, and then hopefully you'll see you'll develop more of an intuition to how to do this. Okay, I'll stop here, and then we can catch up tomorrow. Thank you. Bye-bye.